You slept 9 hours last night. The alarm did not ring. The weekend, the retirement morning, the luxury of sleeping until the body decided it was finished, and the body woke heavy, groggy. A thickness behind the eyes that belongs to 4 hours of sleep, not 9. The fog arrived after the longest rest of the week, on the morning the body should have felt its best. You know this feeling. The reluctance to sit up, the heaviness in the limbs that took the full night of horizontal rest and somehow produced a body that moves more slowly than the one that slept 6 hours on Tuesday. Joints are stiff and the mind is blurred. The cup of coffee that normally clears the residual drowsiness within 15 minutes takes 45. The experience is so consistent that you have learned to expect it. Long sleep feels worse than moderate sleep, and no explanation you have encountered resolves the contradiction. Every source you consult, every physician, every article, every well-meaning family member delivers the same message: sleep is recovery. More recovery should mean more restoration. The body should emerge from the longer rest in better condition than from 7. The universal experience of post-oversleep grogginess contradicts the universal advice about sleep duration, and the contradiction has persisted without resolution for as long as you have been sleeping. A study published in Nature this year followed more than 500,000 adults and measured aging not as a single number, but as independent clocks. One for your brain, one for your liver, one for your lungs, one for your immune system, one for your cardiovascular tissue, each organ aging on its own timeline using imaging, blood proteins, and metabolic markers. The data drew a curve shaped like the letter U. Both extremes accelerated the clocks. Sleeping fewer than 6 hours pushed the biological age of your organs above their chronological age, the damage you expected. Sleeping more than the inherited target pushed the biological age equally. The bottom of the U, the duration associated with the youngest biological age across every measured clock, was narrower than any public health guideline has ever recommended. The conventional recommendation does not sit at the bottom of the curve that measures what it claims to optimize. It sits above it, on the slope where additional hours correlate with additional aging. 9 of the full set of clocks showed the same statistically significant U-shape. The pattern was systemic, not confined to any single measurement technology or any single organ system. Imaging data, protein data, and metabolic data all drew the same shape. The consistency across 3 independent measurement technologies is what elevates the finding from suggestive to structural. A U-shape in brain imaging alone could reflect measurement artifact. A U-shape that replicates across imaging, proteomics, and metabolomics reflects biology. But a curve is a shape. It shows where the damage accumulates without revealing the mechanism underneath. Grogginess offers the first clue. Heaviness after a long sleep, the cognitive fog, the slow blinking, the 20 minutes of impaired function that follow waking, has 2 candidate mechanisms, and both point toward the same conclusion. The first is established in sleep medicine. Extended sleep increases the probability that your body wakes during deep slow-wave sleep rather than during the later stages that naturally precede waking. Sleep cycles run approximately 90 minutes, NREM light, NREM deep, REM, and back. A person sleeping 7 hours completes 4 to 5 complete cycles and tends to wake during the final light sleep phase. A person sleeping the extended duration adds another full cycle and frequently wakes mid-cycle during the deepest portion of slow-wave sleep. Severe sleep inertia follows. The clinical term for the fog, the thickness, the impaired reaction time that can persist for 20 to 40 minutes after waking from the wrong phase. The grogginess is a phase error. You woke at the wrong point in the cycle, and the additional sleep created the additional cycle that put you there. A second mechanism is hypothesized but consistent with the neuropharmacology. Prolonged receptor vacancy during extended sleep may trigger compensatory receptor changes. Neurotransmitter systems that drive waking alertness, norepinephrine, serotonin, histamine, orexin during sleep, are largely quiescent during sleep. Extended quiescence over the longer night is 50% longer than 6 hours. Extended vacancy may prompt receptor upregulation, the postsynaptic neurons increasing their sensitivity to compensate for the prolonged absence of signal. When the neurotransmitters surge at waking, the recalibrated receptors produce a sluggish, oversensitized response rather than the crisp activation of a system that was quiescent for the expected duration. The pharmacology is analogous to caffeine tolerance. Chronic caffeine consumption upregulates adenosine receptors, and the temporary withdrawal of caffeine produces exaggerated drowsiness not because of fatigue, but because of receptor recalibration. Extended sleep may produce the equivalent of a withdrawal effect from wakefulness. Two explanations. Neither definitively isolated as the primary driver. Both predict the same subjective experience. The extra hours feel worse than moderate sleep, and both produce the same behavioral trap. The oversleeper interprets the grogginess as evidence of insufficient rest and sleeps longer the following night, extending the problem. The sensation of needing more sleep is the body's misinterpretation of a problem caused by too much sleep. The signal and the remedy point in opposite directions. If the body misreads stagnation as insufficient rest, what is the mechanism producing the stagnation? And does the brain have a physical limit on how long it can clean? Grogginess tells you something is wrong. The U-curve tells you the damage is real. But neither the fog nor the curve reveals what is physically happening inside your brain during the hours beyond the optimal window. Every gradient-driven system reaches this point. Think of a washing machine. The first rinse cycle removes most of the dirt. The concentration difference between the clean water entering the drum and the soil embedded in the fabric is enormous, so the transfer is rapid and efficient. The second cycle removes less. By the fourth cycle, the water going in and the water draining out carry nearly identical concentrations. Running a fifth cycle does not make the clothes cleaner. The driving force. The concentration differential between the input stream and the substrate has equilibrated. The machine is circulating clean water through clean fabric at the cost of energy, time, and mechanical wear. The benefit reached 0 2 cycles ago. Nothing inside the machine reported the change. The motor hums at the same speed. The water flows at the same rate. Every sensory signal inside the machine says the process is continuing. But the physics of the process, the net transfer of contaminants from fabric to water, reached 0 minutes ago. The machine cannot distinguish between productive operation and purposeless circulation. Neither can you. How does a brain that has been cleaning all night know when the cleaning is finished? Every gradient-driven process reaches this point. The moment when the driving force approaches 0 and continued operation accomplishes nothing. The shower that stopped cleaning 5 minutes ago, the air filter that equalized with the room an hour ago, the dialysis run that cleared the target molecule 2 cycles ago. Each system reaches a physical limit determined not by time on the clock, but by the concentration differential that remains. The question the grogginess raised and the U-curve confirmed, but neither answered, is whether the brain's overnight clearance system operates under the same physics, whether the system that cleans your brain while you sleep has a gradient, and whether that gradient runs out. Now, the clearance system that operates inside your brain while you sleep is not a chemical process. It is a plumbing system. Fluid dynamics operating under mechanical pressure in channels that only open when you are unconscious. The interstitial space between neurons was shown to expand by approximately 60% during sleep compared to waking, and sleep was shown to drive metabolite clearance from the adult brain, as Jia and colleagues established in Science in 2013. The expansion is driven by glial cells, support cells surrounding every neuron, physically shrinking to open fluid channels that remain sealed during the day. Cerebrospinal fluid floods these channels, flowing along the outside of blood vessels in what was subsequently named the glymphatic system, glial plus lymphatic. The fluid carries waste, amyloid beta, the protein fragment that accumulates in Alzheimer's disease, tau, the structural protein whose tangles correlate with dementia severity, metabolic debris from 16 hours of continuous neural activity, the accumulated exhaust of approximately 86 billion neurons across 100 trillion synaptic connections. Estimates suggest the brain produces approximately 7 grams of waste protein per day that must be cleared to prevent accumulation. CSF sweeps through, collects the waste, and drains through pathways at the base of the skull. Driving force is entirely mechanical. Arterial pulsation pushes fresh CSF inward through perivascular channels at a rate synchronized with the cardiac cycle. Each heartbeat generates a pressure wave that propels a small bolus of CSF deeper into the brain parenchyma. Venous drainage on the opposite side pulls spent fluid outward. Between the arterial inflow and the venous outflow, the CSF percolates through the interstitial space, the narrow gaps between neurons that expanded when the glial cells shrank at sleep onset. The physics is identical to groundwater flow through porous rock, a pressure head on one side, a drain on the other, and permeable tissue in between. Flow rate depends on the pressure differential, the permeability of the tissue, and the concentration gradient of the solutes being transported. Channels measured in micrometers, forces measured in millimeters of mercury, clearance measured in milligrams per hour. The system is elegant in its simplicity and brutal in its limitation. It cleans by flowing, and it stops cleaning when the flow stops accomplishing net transfer. So what happens when the flow continues but the cleaning has stopped? Same physics, same constraint. The concentration gradient between fresh cerebrospinal fluid and waste-laden interstitial fluid is steepest at the onset of sleep. The first hours of clearance are the most productive because the differential is large, the flow is strong, and the waste removal rate is at its maximum. As clearance proceeds through the night, the gradient diminishes. The CSF entering the perivascular channels and the interstitial fluid surrounding the neurons converge toward the same waste concentration. The driving force weakens hour by hour. Net transport approaches zero asymptotically. The system does not shut off. The heart continues beating. The CSF continues circulating. But circulation without a concentration gradient is movement without purpose. The fluid enters carrying the same waste concentration as the fluid already there, picks up nothing, and exits unchanged. The mechanical infrastructure is running. The clearance function has completed. The system has reached the point where the driving force for net mass transfer has approached zero. The gradient has a timer. How long until the gradient reaches zero? The point at which net clearance reaches practical zero has not been measured in living human brain tissue during extended sleep. The physics predicts a timer. The exact setting remains unmeasured in vivo. But the fluid dynamics are unambiguous. A concentration gradient that has been equalizing for 7 hours retains less driving force than one equalizing for 3. The population data is consistent with gradient exhaustion. The U-curve turns upward at durations that align with the predicted equilibrium window. The mechanism is falsifiable. If the glymphatic gradient were shown to maintain driving force beyond the optimal duration, the equilibrium hypothesis would fail. The existing animal data points in the opposite direction. Extended anesthesia beyond the normal sleep duration does not increase net amyloid clearance proportionally, suggesting diminishing returns consistent with gradient exhaustion. The physics predicts diminishing returns because the mathematics of diffusion predicts diminishing returns. The rate of mass transfer across a concentration gradient is proportional to the gradient itself. As the gradient approaches zero, the transfer rate approaches zero at the same rate. The relationship is asymptotic by the governing equation itself. The mathematics of diffusion, not a rhetorical convenience. And then, a second analogy earns its precision. Imagine opening every window in a smoky room. The initial rush of outside air clears most of the particulates in the first 10 minutes. The concentration differential is enormous, and the cross-ventilation is correspondingly strong. After an hour, the concentrations have nearly equalized. Here is the dimension the washing machine did not reach. The smoke particles that remain after equilibrium continue to deposit residue on surfaces, walls, furniture, fabric. Extended contact time between residual pollutants and surfaces is itself a damage mechanism, distinct from the initial exposure. The hours beyond the optimal window may not be adding clearance. The physics predicts they are extending contact time between residual waste proteins and the neural tissue. Those proteins damage when they remain in sustained proximity. Amyloid beta in sustained contact with synaptic terminals promotes oligomerization, the aggregation of individual protein fragments into larger toxic clusters. Tau in sustained contact with neuronal microtubules promotes hyperphosphorylation, the chemical modification that causes tau to detach from the structural framework it normally stabilizes. Extended contact time accelerates the conversion. The hours beyond equilibrium are hours during which the residual waste is actively converting from individual fragments to pathological aggregates. Gradient physics resolves the brain's ascending slope. The organ most directly dependent on glymphatic clearance shows the steepest U-shape because the clearance system that serves it has the most defined physical limit. But the physics that governs the brain cannot explain the immune system's ascending slope. The immune system does not rely on glymphatic clearance. Something else is aging the organs outside the skull. What damages organs that do not depend on CSF flow, and why does each organ draw a different curve? Answers arrived in the same Nature paper. The finding the multi-consortium demonstrated, with Junhao Wen at Columbia University, that makes the full set of clocks more than a number. The U-shaped curve is 23 overlapping curves, each organ drawing its own U, each with a slightly different nadir, each with a different slope. The brain's proteomic aging clock showed the strongest U-shape of all, and here the specific numbers emerge. The aggregate optimal window across every measured clock emerged here. Below the conventional target, inside a narrower range than any guideline has recommended. The brain's optimal sits at 7.7 hours for men and 7.8 for women, a sex difference that aligns with known differences in glymphatic flow, where estrogen modulates aquaporin 4 expression in the astrocytic end feet lining the perivascular channels. Immune tissue tells a different story. Extended immobility during long sleep allows inflammatory cytokines to accumulate in tissue compartments that would normally be cleared by the gentle mechanical agitation of waking movement. The shifting of position, the walking that contracts muscles surrounding lymphatic vessels and drives the lymphatic drainage the immune system depends on. The immune patrol that clears senescent cells and precancerous mutations runs on lymphatic flow, and lymphatic flow requires muscular contraction to pump fluid through one-way valves in vessels with no intrinsic pumping mechanism. Horizontal stillness beyond the optimal window approaches the boundary where surveillance stalls, and the extended hours push into the morning period when overnight immune debris should already be mobilizing toward drainage nodes. Well, growth hormone delivery completes in the first half of the night. The remaining hours are the period during which the rebuilt cells should begin their surveillance patrol, not continue dormant. Oversleeping delays the launch. The 3 a.m. discussion described the cortisol architecture that ramps the immune system from overnight quiescence back to daytime vigilance. What happens when the reactivation signal fires into a body still asleep? The patrol that should have resumed at 6 does not resume until the extended sleeper finally rises. Additional hours during which overnight debris accumulates in compartments the lymphatic system cannot reach without muscular assistance. Debris accumulates in tissue spaces, lymph nodes, and perivascular compartments. Inflammatory markers, interleukin-6, reactive protein, tumor necrosis factor, alpha, rise incrementally with each additional hour of immobility beyond the optimal window. The aging clock accelerates. Because the morning reactivation was delayed by hours, the body spent resting past the point of restoration. Each organ has a different vulnerability, and the vulnerabilities do not overlap. The mechanism that damages the brain during extended sleep is unrelated to the mechanism that damages the immune system, which is unrelated to the mechanism that damages the liver. Sleep duration, sleep consistency, and sleep timing are 3 independent variables acting on different organ systems through different physics. The standard advice compressed all 3 into a single number. Brain tissue is most damaged by duration extremes: too short, insufficient glymphatic clearance; too long, gradient stagnation and extended waste protein contact. Immune tissue is most damaged by excess duration, specifically extended horizontal immobility suppressing lymphatic-dependent surveillance. Liver tissue showed a third pattern: less sensitive to how long you sleep, more sensitive to whether you sleep at the same time each night. Variable wake times desynchronize the liver's internal clock from the master timing signal in the suprachiasmatic nucleus. The SCN recalibrates within a day when the wake time shifts. The liver clock takes 2 to 3 days. Its metabolic rhythms running on enzymatic cycles with longer half-lives than the SCN's neural oscillation. The immune clock, dependent on the slow turnover of immune cell populations and the gradual redistribution of cytokine profiles, takes 5 to 7 days to fully adjust. Sleeping the standard duration on weekdays and extending on weekends produces a weekly desynchronization cycle that forces the slower organ clocks to perpetually chase a timing signal that moves before they reach it. Cardiovascular tissue ages through a fourth mechanism: the autonomic transition stress of waking. Heart rate rises, blood pressure increases, vascular tone shifts from parasympathetic relaxation to sympathetic activation to sympathetic activation. A consistent wake time produces a consistent transition the vascular endothelium adapts to. An irregular wake time produces irregular transitions, the mechanical stress on coronary arterial walls arriving at unpredictable intervals. Unpredictable mechanical stress accelerates endothelial aging. Adults who combined long weekend sleep with irregular schedules showed the steepest acceleration on their cardiovascular clocks, the compounding effect of two variables acting on the same tissue through different damage pathways. Fixed wake time is the single most protective variable for the consistency-sensitive organs. The suprachiasmatic nucleus, the master clock behind your eyes, requires a consistent morning light signal to maintain its oscillation. A fixed wake time delivers a fixed calibration pulse through melanopsin-containing retinal cells that respond specifically to the blue-weighted spectrum of morning daylight. The downstream organ clocks lock onto this signal and stabilize at their optimal phases. Shift the wake time by 2 hours on Saturday, sleeping until 9 instead of 7, and the SCN adjusts within a day. But the liver clock takes 2 to 3 days to realign. The immune clock takes 5 to 7. By the time the immune clock has adjusted to the weekend schedule, Monday has arrived and the alarm resets the cycle. The metabolic timing never stabilizes. The organ clocks never reach their floor on the U-curve because the floor keeps moving beneath them. What does 52 weekly recalibrations per year do to an organ clock that takes a week to adjust? Every Monday is a miniature jet lag, a forced realignment that the brain handles in a day and the immune system handles in a week. 52 weekly realignments per year, a body that spends more time adjusting than adjusted. If every organ responds to a different variable, how does the single number on the alarm clock serve every measured clock simultaneously? Arithmetic answers it. Sleep latency, the time between lying down and falling asleep, averages 12 to 20 minutes in healthy adults over 50. Nighttime awakenings accumulate 20 to 40 minutes in adults over 60. A person who goes to bed at 10 p.m. and sets the alarm for 6 a.m. has created an 8-hour opportunity window. Subtract 15 minutes of average latency and 30 minutes of accumulated fragmentation, and the actual sleep duration inside that window is 7 hours and 15 minutes, inside the 6.4 to 7.8 hour optimal window. That person sits near the bottom of the U while believing they sleep the inherited target. The number was wrong because it measured opportunity while the biology measures duration. Every sleep guideline you have ever read tells you how long to stay in bed. The U-curve measures how long you actually sleep. The two numbers diverge by 30 minutes in a healthy 30-year-old and by an hour or more in a healthy 65-year-old. The guideline and the biology are measuring different things, and the gap between them widens with age. Perceived sleep and actual sleep diverge with age. A 30-year-old may lose 20 minutes to latency and fragmentation. A 65-year-old may lose 60. The same opportunity window delivers different actual durations at different ages, and the recommendation applied identically to both. The irony, the 65-year-old who sets the alarm for the inherited target and complains about not getting enough sleep is sleeping inside the optimal window. The 30-year-old following the same target with less fragmentation is sleeping above it. The number was accidentally protective for the population it frustrates most. Older adults who believe they are failing to achieve adequate rest, and potentially harmful for the population it fits most comfortably. Younger adults whose efficient sleep carries them above the window the U-curve identified. Weak. I ran this myself. Lights out at 10:15, alarm at 5:45. 7.5 hours of opportunity. The sleep tracker registered 6 hours and 52 minutes of actual sleep, with 14 minutes of latency and 24 minutes of accumulated wakefulness across 3 brief arousals. 6 hours and 52 minutes, inside the optimal window the nature data revealed, below the gradient exhaustion threshold, above the minimum clearance requirement, the mornings were clear. The fog was absent. Same schedule 7 days a week. The SCN received the same signal every morning. The liver clock stabilized by midweek. The immune clock stabilized by Thursday. The adjustment period was 3 days. The first 2 mornings felt early. By day 3, the body anticipated the alarm. By day 7, the alarm was a confirmation. The weekend tested the commitment. Saturday morning, 5:45, no obligation to rise. The body rose anyway. The grogginess that used to define Saturday mornings was absent because the Saturday wake time matched the Tuesday wake time, and the liver clock that would have spent Monday recalibrating never had to recalibrate at all. The experiment was not comfortable on day 1. 5:45 on a Saturday morning with no obligation is a test of whether you believe the physics. By day 10, the question dissolved. The body had locked onto the signal so completely that the alarm became redundant. The SCN woke me 3 minutes before the alarm. confirmation that the biology and the schedule were synchronized. And then, a third analogy for the gradient, drawn from the body itself: your morning shower. The first 5 minutes under the water remove the accumulated film of the night, dead skin cells, sebum, bacterial residue. The concentration differential is high and the transfer is rapid. By minute 10, you are standing under warm water flowing over clean skin. The cleaning finished 5 minutes ago. The warmth feels productive. The perception of benefit has decoupled from the physics of benefit. The 20th minute is not cleaner than the 5th. But the warmth makes it difficult to step out, and the sensation of warmth is indistinguishable from the sensation of cleaning. The shower does not announce when it stops being productive. Neither does sleep. The transition from restoration to stagnation is silent, comfortable, and entirely invisible to the sleeper. The 9th hour of sleep is the 20th minute of the shower. Warmth feels like recovery. The subjective sensation persists long after the physics stop delivering value. The glymphatic gradient equilibrated hours ago. The immune patrol stalled in lymphatic channels waiting for vertical posture. The organ clocks are drifting upward on curves the body cannot feel from inside the horizontal comfort of a bed that stopped restoring hours ago. You feel warm, horizontal, and free of obligation. The body interprets these signals as recovery continuing. The biology shifted from recovery to stagnation somewhere around hour 7. Stagnation and rest feel identical from the inside. Everything after that is warm water on clean skin. Fixed wake time protects the consistency-sensitive organs. Controlled duration protects the gradient-sensitive brain. Vertical posture in the morning protects the immobility-sensitive immune system. 3 variables, every measured clock. One number that was inherited from a century of labor scheduling, a partition that divided the day into 3 equal parts the body never endorsed. The glymphatic system was not discovered until 2012. The U-curve was not drawn until the data grew large enough to distinguish both slopes. 500,000 adults and organ-specific aging clocks revealing a window narrower than any guideline had recommended. Your organs age at different rates, through different mechanisms, with different sensitivities to variables. The standard advice never distinguished: duration for the brain, consistency for the liver, morning mobility for the immune system, transition timing for the cardiovascular walls. The biology is narrower than the advice. It always was. And the narrowness is not a limitation. It is precision. 6.4 to 7.8 hours. A gradient that exhausts. Organ clocks that tick independently. A U-shaped curve that punishes both sides of the error equally. Your morning alarm keeps every measured clock synchronized, the gradient finite, and the biology within the window. The inherited target overshot.